Here we're going to do an example hypotheses question on proportions. This question is in your PowerPoints. A study found that in 2005, 12.5% of workers belong to unions. Supposing a sample of 400 workers is collected in 2006 to determine whether union efforts to organize have increased union membership. So that what we want to find out if there's been an increase in the proportion of people that belong to the union from 2005 to 2006. The sample results show that 68 of the 400 workers belong to unions. Use a value of alpha of 5%, which is the probability of a type 1 error, to see if there has been an increase in membership from the 2.5% of last year. So I guess we're assuming we're in 2006, and the information we have for 2006 is 68 of the 400 workers sampled belong to the union. So what does that look like? Let's just have a quick look to see what that looks like. So this is all the potential people that could belong to the union. We've taken a sample here. They're telling us they've taken a sample of 400 people. So the sample size is 400. And they found out of these 400, let's do the sample proportion that belong to the union is in fact, well, it's going to be 68 of 400. So it's going to be 68 divided by 400. And what does that come to? We just go into Excel and put that in. We're going to find out that that value is in fact 0.17. So 17% of the sample belong to the union, but we have to see if that means that more than 12.5% belong to the union as a whole, not just from that sample. So what they're asking us to check again is we want to see if there's been an increase in the membership from the 12.5% of last year. So what I'd like to check is this. I'd like to check to see, or what they're asking us to check is to see if the proportion in 2006 is now greater than it was last year. And last year it was 0.125. So this is what they're asking us to check. Now, as you can see, that they're not asking us for greater than or equal. They're saying an increase. An increase does not include equals. So this is the hypothesis they want us to check. Because this does not have an equals in it, this is an alternative hypothesis. So this is going to be HA. So in fact, in this question, they've given us the alternative. They're not obliged to always give us the null hypothesis. The null hypothesis that goes with this would be the exact opposite, and that's going to be the one that has the equals in it. So it's going to be HA. And that's going to be the proportion is less than or equal to 0.125. Now, even though the original statement they've given us that they want us to solve is this guy in here, they want a yes or no answer to this, we will still proceed and as we've done before, we will find an answer for the null hypothesis. And that once we have an answer for the null hypothesis, we automatically get an answer for the alternative hypothesis. And you'll see what I mean as we go through the question. So when we look back at what we did before, and I gave you the breakdown in the last video, you'll be able to see that this is going to be a one-tailed test with rejection to the right-hand side. However, before we proceed, we ought to check for proportions. We need to check really if n times p is greater than or equal to 5. And we also need to check if n, so that's times p, if n times 1 minus p is greater than or equal to 5. Now what do we have? We have, in our case, n is 40, and times p is 0.125, which is greater than or equal to 5. So we're good there. And then this is going to be 40 times 1 minus p. Well, if p is 0.125, 1 minus p is 0.875. And again, if you do the calculation, you'll find out that that is indeed greater than or equal to 5. So that means that we can go ahead and we can actually use the results that we have. In fact, 40 times 0.125 is exactly 5. And so that's good enough. It's greater than or equal to 5. And 40 times 0.875, sorry, is actually equal to, well, it's a lot greater than 5. 40 times 0.875 comes to 35. So the first one comes to 5, it's greater than or equal to 5. The second one comes to 35, which again is greater than or equal to 5. So let's proceed now and calculate whatever is necessary to come up with our solution. Now, we know, let's put 0 in the middle, with proportions, the distribution will be a z distribution, so long as these two conditions hold, which they do. And this hypothesis is going to give us a one-tailed test with rejection out to the right-hand side. And the critical value is going to be in here. So let's see, the rejection is going to be out to the right-hand side. So it's going to be our reject H0 zone. And the other side is going to be the do not reject H0 zone. So let's go down here. So this is do not reject H0. Do not reject HO or H0 or H0. So the critical value, if you remember, for a one-tailed test for proportions, is going to be z of alpha over z of alpha, sorry, not z of alpha over 2, because it's a one-tailed test, so it's just going to be z of alpha. And we were told that alpha is 5% up here. We were given that alpha was 5%. So let's calculate the critical value. So the critical value here, the formula we're going to use to calculate it, is going to be, well, there's several ways of doing it, so let's just use one way. It's going to be norm dot s dot inverse Remember, XL works with the area to the left, so if the area to the right is 5%, the area to the left is 95%. And that's it. Now, remember that we'd always have a normal distribution for these guys. I can draw it in if that makes it easier for you. So you can see that the area, the rejection area was given as 5%. So this is 5% over here and 95% to the left, if that makes it clearer for you. Let's just pop over to Excel to do this calculation. So so in Excel, let's do equals norm.s.inverse and 0.95. And what does that give us? 1.64. That's fair enough. 1.64, 1.65. Let's go back over to here. And so this value in here is in fact going to be 1.6. Let's go for 1.65. Okay, so all we need to do now to actually complete this is to find out the value of the test statistic. Now, if you remember, the value of the test statistic for a proportion question, or the standardized test statistic that I called it before, just remind ourselves, is going to be P bar, and P bar is going to be 0.17, minus P from the null hypothesis. Well, the proportion that comes from the null hypothesis is the proportion from the null hypothesis is whatever value is in here in green, which would be 0.125, and then we're going to divide that by the square root of P of h0. Again, P of h0 we said is going to be 0.125. We're going to multiply that by 1 minus P of h0. And we're going to divide everything in the square root sign. We're going to divide this guy by the sample size, and the sample size was 40. So let's do that over here. P bar is 0.17. There you go. That's P bar from up here. And minus P of h0. Well, P of h0 is going to be P from h0, whatever value is in there. Don't worry if it's less than or equals, greater than or equals, or equals. That's why in fact we have the equal sign in here, so we can take that as a starting point. Whatever value is in there, we just pick that value. So that's going to be minus 0.125. And then we're going to divide that all out by the square root of 0, P of h0, which is 0.125 as above, multiplied by 1 minus 0.125. And we're going to divide that by the sample size. So this guy is going to be divided by the sample size, which is 400. I think I might have said 40 earlier. It's actually 400. Okay, yeah, it's 400. I'm not very good at writing with this with the mouse. Okay, so let's do this calculation. Should we just pop over to Excel to do this calculation again? So let's just pop over to Excel. And let's do the calculation. So it's going to be, I'm going to do it in two parts. I'm going to do it the numerator, the top part, which is going to be equal to 0.17 minus 0.125. Okay, and the bottom part is the square root. So I'm going to do equals, sorry, I'm going to do equals SQRT square root of 0.125 multiplied by 1 minus 0.125, close parentheses, and we're going to divide that by the sample size, which we said was 400, and close the parentheses. And let's see what that gives us. So that's the numerator, that's the denominator. So I have to divide those out. So it's going to be this guy divided by this one. And that gives us 2.72. So let's go back. So this guy in here equals 2.72. So where does that actually fall? Because that's our test statistic, and the 2.72 falls where? Well, if this is 1.65, 2.72 falls somewhere over here. It falls in the reject H0 region. So let's go up and see. We're doing the test on H0, so we're going to reject H0 in this case, and we're going to go with the alternative. So even though we may have been concerned that the original assertion they gave us, or the original item they wanted us to check was this, we ended up still doing the test the same way, running the test on the null hypothesis, finding out that we're going to reject the null hypothesis, but that's fine, because if I reject the null hypothesis, then I go with the alternative. It has to be one or the other. It can't be both. Both of these can't be right, and neither of them will be wrong. It must be that one is right and one is wrong because they're complete opposites to each other. So if I get a result for one, then I automatically get a result for another. It's like if I flick a coin in the air and I look at the top of the coin when it comes down and the top of the coin is a head, I don't have to look below to see that it's a tail. I know it's a tail below if it's a fair coin. So don't worry about them giving you a hypothesis, which is the alternative. You still run it exactly the same way. You don't try and change any of the conventions and you'll come up with the correct answer. So that approach we just used, in fact, is the critical value approach. This approach here is called the critical value approach. And remember, I showed you how to do a second approach. And the second approach is the p-value approach. So let's actually solve this problem now using the p-value approach. So for the p-value approach, let's put p there, p-value, so we know what we're dealing with. The p-value approach, let's just write things out again. We need the test statistic, and the test statistic we said is this 0 in the middle, and this is z. And we need the test statistic, and the test statistic we already established was plus 2.72. 2.72. And we need to find the p-value is going to be this area in this right-hand tail to the closest tail. So we need to calculate all of this area in here. And if you look back at the previous video, I gave you a template for calculating this, and this is going to be 1 minus norm.s. Let's go with it. Norm.s dot dist. We need the test statistic, which we said is 2.72. 2.72. And then we're going to put either a true or a 1, gives us the same result. And let's see what that gives us. Let's jump over to Excel again. So let's just so in Excel, I want to calculate 1 minus norm dot s dot dist. Where's that? Right there. And in fact, I can either put in the 2.72 or I can actually cell reference that, which will give me a more accurate answer. And it's up to you how you do it. And that's going to give me 0.003. Where's that as a percentage? So we can compare it to the 5%. Let me make that a percentage. I'm just going to click on this guy up here to make it a percentage. It's coming up with 0%, and that's because it's so small. Let's actually move the decimal places. It's actually 0.33%. It's less than 0.5%. So, okay, let's go back. And now we know what the answer to this is. So the answer to this is, it's a very small value. It's 0.33%. And to solve this problem using the p-value approach, I need to check to see the result, to see if alpha is greater than or equal to the p-value, in which case we reject H0, or if alpha is smaller than the p-value. Well, in this particular case, we have alpha, and alpha is 5%. We have the p-value, and the p-value is 0.33%. So clearly here, alpha is greater than the p-value. Alpha is greater than the p-value. And if you look back at the results I told you before, that implies that we should reject H0. So this is using the second approach of using the p-value, and we're coming up again reject H0, and that was exactly the same result we used when we used the critical value approach. Again, it was reject H0. So two alternative methods, they will always give the same answer. Whether you use the critical value approach or the p-value approach, you will always get the same answer. If you get a different answer, you've made a mistake.